Hi and welcome to this video presentation. In this video I will go through the reasons and the basic history for quantum mechanics and a short introduction for wave-particle duality. So the question which started quantum mechanics was asked by ancient Greek philosophers, and that question was, if you have a rock, how many times can you divide this rock before it becomes indivisible? And there were different schools. Some people said you can only divide them to a certain level, and so came the word atomos, which I believe in Greek means undivisible, meaning you can't split it any further. So the other school was there is no limit for splitting stuff. There is no limit for splitting a stone, since you will only get half of what you had before. So for example, if you have a rock, you will only get half a rock, then a fourth a rock, an eighth a rock, and so forth. Until infinity. You can't have a limit for it. So in the 1800s, people started to realize that stuff was made up of elements. There were gold, there was iron, and so forth. And people knew that if you have iron ore, you cannot make gold from it. You can only make iron from it. So there was some kind of difference between these elements. They were built up. They had their own construction. So alchemists throughout many hundreds of years tried to find a solution for how to make gold from common metals. And no one couldn't, because people have actually achieved it now in particle acceleration facilities, but it's quite expensive. So nobody quite couldn't do it. So John Dalton in 1803 said that elements have building blocks. Elements are built up by atoms, and they can go together to create element, right? So these atoms can create substructures, can create molecules and all that stuff. So J.J. Thomson in 1897 concluded and did an experiment where he had a glass tube like this one, and to this glass tube he attached a current. Like this. And on top of this glass tube he put a positively charged metal piece, and on a negative charge on the bottom. And then he proceeded to fill up this glass tube and shoot it with hydrogen gas. And he noticed something quite interesting. That the hydrogen that came in here, some parts of it actually stirred off to the positive, and he had enough information about physics that he understood the saying that equal repel and opposite attract. So he knew whatever got to the positive charge needs to be negative. An electron, for example. But then he didn't see anything go to the negative charge until he looked closer. And there he found a small attraction to the negative plate. So there was something positive, for example a proton. But he concluded, since there was such an immense difference between how vastly the atoms, the force between the atoms, the electrons to the positive plate, was much greater than the force between protons to the negative plate. So he concluded that whatever is negative must be much smaller than to whatever is positive. So the positive must be much greater, because the heavier something is, the harder it will be to steer it off direction, steer it off course. So he concluded a model that the atoms looks like this, like a cookie sort of. you have small dots in the middle, and those dots equals the dots is the electrons, the negatively charged particles. And surrounding this you have the protons. So the crust, if you so will, is the protons. Now that was a basic idea of how an atom looked. And of course, if you have studied some kind of physics or chemistry or whatever, you will understand that this picture is not entirely true. So we will get to that just in a second. Time passed and we started to get a more sophisticated version of how an atom is, how an atom looks and how it's built up, the construction of an atom. So the thing that most folks are taught in school is that an atom is constructed with a core of positively charged particles, protons and neutrons. So the core is positively charged, and surrounding this core you have electrons in different circuits. Sort of like a small solar system. But the question here then was, we know that charges that accelerate will lose mass due to radiation. So charges that accelerate will radiate and lose mass. And you see, if you attach an electron here, we have another one here. Let's take this electron. Here's the electron. If this electron goes around this circuit, it will accelerate due to the fact that, let's say that this electron is a ball, for example, and this is the string. So if you cut this string whilst the electron is going through the circuit, you will see that the electron wants to leave the system with a velocity v. But it goes through this circuit here. So it goes through this circuit, right? So it is actually pushed inwards with an acceleration. That is centrifugal acceleration, I think it's called in English. So you see, the electron must accelerate, and since it has a charge, it will lose mass. So we started to conduct experiments. One of the most famous one is called the double slit experiment, which basically is you have a wall with two doors. And back in the end of this experiment you have a cannon that shoots out photons. We'll get more into depth about what photon is later in this video. So this cannon shoots out photons randomly. And on this wall here we have a detection scanner, so it feels when something hits it. So when you shoot out waves, here comes the wave. If the doors are of the correct size, meaning they are not too big, not too small, they will work as a new, they will create disturbance in the wave and actually create two new waves, like this. So you get two new waves coming out from these doors. And as you can see, these waves overlap. And the waves looks like this. And the crests or the tops of the wave, if those two tops meet, they will become bigger, one big top. If two of the lower parts of the wave meet, they will annihilate each other. So you can have, this is called interference, by the way. So you can have interference that is positive and interference that is destructive. So constructive and destructive interference. So by this way you will get an interference pattern that looks something like this. We have one big spike here in the middle, and then you have small things. And these things, they go to zero. There's no interference here. These 0 points, the minimum points, they are where destructive interference occur. So two waves annihilate each other, essentially. And these big points, here, 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 and here, they are the points where the crust or the top of the waves contribute to each other and create constructive interference. So we know that waves, they have interference. So we did the same experiment, but with electrons. We got quite a surprising answer. You see, if you have the same experiment, you have this cannon here that shoots out electrons. Let me just move the camera so you can see it a bit better. Like that, perfect. And you have the same detection screen right here. And if you shoot off electrons, which we have always thought of as particles, you would imagine that they would just hit at random. And where the doors are, you will get a bigger detection of electrons, right? Sure, so if you have some sort of way of measuring these electrons, you will see what you would imagine. Some electrons here, some here, some here, some pretty much everywhere. Even randomly distributed, if you so will. But so it's sort of like this. This is how it pretty much looks. This is what it looks like, roughly. But that is what happened when we watched the experiment. But if we did the experiment again, up here, and we did not observe the experiment whatsoever, we found a surprising answer. Yeah, that the electrons that is shooting, that is fired against these doors, they created interference. They interfered with each other. So they build up some here, not any there, a bit more here, a lot here, and some there, and some there. Sort of like that. So they created interference when you did not observe the experiment. And that is one of the questions about quantum mechanics. What happened there? Why were there interference here but not there? And the answer is rather surprising. It's because the electron is in fact in a superposition of actually going through that door and that door at the same time. It's a very weird and absurd way of thinking, I know that. But what I mean by that is the electron did not go through that door nor that door. It did not go through both at the same time, neither did it go through any one of the doors. It did go through in a superposition of going through that door and that door. And by doing that, it can have interference. I will get into more depth about this in a future video. So now that we understand that, well, electrons, they can behave as waves. Even though we always have thought of electrons as particles, how about photons? Let's take a new page for that. So let's imagine that we have a piece of metal here. And on this metal we shine light. This is the notation for light in this video. And when we shined light on this piece of metal, we saw something strange. Electrons started to leave. And for this to happen, we found that the light needs to have a certain frequency of around UV light, ultraviolet light. So the frequency needs to be around ultraviolet, right? So for this frequency 0.0, nothing will happen. But if you surpass this frequency 0.0, you will have electron submission. So what happened here was described by Einstein as the photonic electric effect. The photon electric effect, which he described in a new sort of way. He said that what happens is that photons, which we have always thought of as light, can in fact behave like a particle. Okay? So he described this by saying that light is made up of photons. And the energy for a photon is Planck's constant multiplied by the frequency of that photon. So the only way to increase or decrease the amount of energy from a photon is to change the frequency of the light wave. So a higher frequency will naturally give you a higher energy rate, and a lower will give you a lower energy. Great. So he described this in a way of saying that light comes in packets of Planck's constant. Light is quantized to each other. And why only certain frequencies of light will shoot off an electron is due to this effect. The light needs to have a certain amount of energy in order to break the binding force the electron has to its atom. And if that force is greater than the binding force, the electron will have a little bit of excess energy in terms of kinetic energy and will be able to leave the metal plate. But if the force from the atom equals exactly the binding force between the electron and the atom, let me just rephrase that. If the energy of the photon is exactly equal to the binding force of the electron to the atom, nothing will really happen. The electron will leave, but it won't have any kinetic energy, so it will just stay there pretty much. So the energy for a photon, HF, needs to be greater than the binding energy. So the question that came to everyone's mind was, how did the photon obtain its momentum if the photon is massless in order to knock the electron out of its orbit? Because we know from classical mechanics that momentum, P, equals simply mass times velocity. And since a photon has no mass, it will essentially not have any momentum, because any term multiplied by 0 equals 0. But we have this famous formula that E equals mc squared. And if you rearrange this equation, you will find that mass equals simply E over c squared. And if we put this new mass term into this equation, you will find that P equals E over c squared multiplied by c, which essentially just equals E over c. And we have found a new term that in the earlier experiment, that the energy for a photon is simply Planck's constant times its frequency. So we put this new energy term into this equation, you'll find that P equals HF divided by C. So this is how you find momentum for a particle which has no mass. So light can actually have momentum and behave in that way as a particle. So Louis de Broglie, I don't know how you pronounce his name, said that light, which we have always thought of as a wavelength, can behave like a particle. Can a particle behave like a wavelength? And remember now, this is a very dangerous mindset to have. Boy, wouldn't it be nice if, for example, wouldn't it be nice if I did not have to pay taxes but had free Medicare? So that sort of logic does not always work, but in this case it actually did. So he said that lambda, which is the wavelength of a particle, or in this case now, the wavelength of a particle, let's take that, equals Planck's constant divided by momentum. And as we said earlier, momentum is simply mass times velocity. So you can rearrange this formula for a particle with mass, something with mass, as lambda equals h over mass times velocity. And this actually checked through. This was concluded as true. So essentially, anything in the universe which has mass has a wavelength. If you threw a ball, that thing will have a wavelength. But why you won't see that wavelength is because Planck's constant is a very small number. So your lambda will be a very small number. Indeed. So that wavelength will be so so small that it will be practically impossible to measure or observe. So that is my end conclusion. That is the reasoning for quantum mechanics and a basic introduction to wave-particle duality. Thank you for watching. Have a great day.